I welcome you once again to another video section on analysis. So this is video series 6, if I'm not mistaken. So here in this case now we have uniform convergence. This is what we want to consider for today's tutorial session. Now I from our previous video I said we are going to state the definition and the theorem for uniform convergence. Now let's start with the definition. So for the definition there, we need to start by saying, okay, a sequence of function is given, or we say a sequence of function is said to converge uniformly when. When do we say that a sequence of function converges uniformly? So I think that's what we need to define here. Okay. Um, let's start by saying, okay, let me try to give a very clear definition to this. Let me put it this way. A sequence of function. So don't just write the sequence of function is set to. You need to write that okay sequence of function, right? And how do you write a sequence of function? Fnx, right? In the curly bracket. A sequence of function fnx is said to be uniformly convergent, or is said to converge uniformly. Is said to converge uniformly, okay, to a particular function f. You remember this f now, f of x, to a particular certain limit, right? F of x is the limit. This f of x here is the limit. Is that clear? It converges to, if I find the limit of a function now, fnx, and then the result is equals to 2. That means the limit here is 2. And this thing always converges to fnx. F of x rather. I've given you the explanation in the first or in the second video also. The second video. Now, the sequence of function fnx is said to converge uniformly to a particular limit f of x. Okay? Such that such that um we have such that if you actually have let's say we have a natural number n that is depending on epsilon, but in that case I'll just, okay, you can try to put it that way if you want to cram, but I'll just advise you to go straight to the point. A sequence of fnx is said to converge uniformly to f of x, such that if you take the absolute, okay, take the absolute of that sequence function minus the limits. Remember that we've done something like this in maths 2 and the analysis 2 also, such that if you take the absolute of fnx minus the limit, the limit value, and here in this case we are not making use of limit value. Our limit value here simply represents f of x. So understanding matters. So you just be like, why is f of x here? You don't really understand. It actually follows what you have been doing since reanalysis, what you have been doing in reanalysis 2 and 3 also. So you always have a sequence here, right? Then minus the limit. But here in this case, our limit is already, this is our limit value, as is actually represented as f of x. Okay. So we are using f of x to represent that, such that this is always less than epsilon. And if you want to complete this definition, you know how to do that. I think you should have the full definition in your notes. You have to say, okay, for given for a given epsilon greater than 0, all those things, such that we have a small natural number n that's always greater than n. So you know where to put that. But at least this is just what we need for the definition. A sequence of function fnx is said to converge uniformly to f of x if the absolute of this minus this is less than epsilon. So I think that's just fine. And if you want to give the full definition, you can go ahead, okay? Such that there exists epsilon greater than 0. Sorry, you can actually put it that way, that okay, a sequence of function fnx is said to converge uniformly to f of x for every given epsilon greater than 0. Do you understand? We can actually find a natural number small n depending on epsilon, okay, such that if this n greater than big N, okay, such that if n be greater than this big N, then there exists the absolute of fnx, or you say then it follows that the absolute of fnx minus f of x is less than epsilon. Okay, I think that's all we have to do here already. That's fine. But the major thing is we need to try an example. So let me state the theorem, then we can go ahead and bring in examples. So in this case now we have the Weierstrass theorem for this case. So for this theorem here, we need to okay, we also have what we call the Cauchy criterions for uniform convergence also before I move straight to the theorem. But we still need to consider this because when you have the Weierstrass M test, the majorant test, or the theorem itself, you can also state this theorem. What does this theorem state? Okay, this theorem actually says that let fnx be a sequence of function as usual. This is a sequence of function, okay? And then suppose there exists suppose there exists a let's say a positive number. It must always be a positive, not negative. Suppose there exists, this sign for there exists. Suppose there exists a positive number majorant test, right? A positive number we always represent it as capital letter M with subscript of n. Do you understand? Suppose there exists a positive number Mn, capital letter M of this nature, then subscript n. Okay? This Mn is a positive number, right? So it can be 1 over n, it can be 1 over e raised power of n, it can be anything, but it's a constant. Take note that it's a constant, right? Because n is just like a term one. You have 1 over 1, 1 over 2. So suppose there is a positive number Mn, okay, with let's say with okay, when the absolute of since it's a positive number, that means you take the absolute of that series of function given to you, so you not end up having any negativity for the mn, such that suppose there exists a positive number mn with this absolute, you always take the absolute of this to be less than or equal to that mn that I just explained, then it follows that it follows that the series of that sequence of function, okay, it follows that the series of that sequence of function given to you, the series of fnx, okay, sorry, now let's just say, okay, it actually follows that yes, the series of that sequence of function given to us here converges. It converges what? Uniformly. Then it follows that the series of that sequence of function converges uniformly. It converges uniformly if, under what condition? If you also take the series of that mn, if the series of that mn converges, that's all. So that means what we want to use in this theorem now is just this expression here, show that this one is true. But if you have been able to show that this one is true, and then you can also show that this one converges, so what happens? The question given to you, the series of that function given to you converges uniformly. Because I think this should give us our final answer. This expression here is what will actually give us our final answer. This converges uniformly. This is what we want to show. Okay, we want to show that a series of a function converges uniformly. And to show that, you need to use this first. You must be able to show that the absolute of this one is true. If this is true, and you can as well show that the summation of that positive number mn converges, then what happens? Let's say you actually find your mn to be equals to 1 over n squared, and then you now show the series of mn, or it's not a must even show the series. You can also say that, or if the limit as when n tends to infinity, but this is also the same thing. If the limit as when n tends to infinity of mn converges, because if you take the limit as when n tends to infinity of 1 over n squared, that expression there converges. What happens? The series of that fnx converges uniformly. But to really understand this clearly, we need to take an example. So I'm looking for a very clear example to use in this case. We have a lot of examples. But I would like to pick a very nice one so that at least we get it once and for all. So I think this should be example 6. So far, so good. We want to consider example 6. And then for the example 6, I would like to take a question which says that we should show that the particular series converges uniformly. Okay, I think I have a question here. I've seen a particular question here which says, let's try this out. Okay, okay. I'm trying for a particular question. Do you have any question there? Okay, 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 okay. So just hold on. 312 assignment converges uniformly. Okay, next. Just okay, I've seen a question here. This is what I'm trying to look for. This particular questionnaire says, consider fnx to be equal to nx divides 1 plus n squared x squared. Please pay full attention to this. Okay, x is a member of real numbers. That's from negative infinity to infinity. Okay, then show that there is no natural number n such that the absolute of fnx minus f of x is less than epsilon holds, such that this holds for epsilon greater than 0. So I believe you seeing this expression here will take you straight to the definition for what? For uniform convergence. So you know that it is somehow related to each other. So to deal with questions like this, okay, let's say we want to prove. Okay, so in this case now we have at first we actually given fn of x to be equals to nx divides 1 plus n squared over x squared. So this is what we have. Now, if you have something of this nature now, we need to find our big N. But before you do that, you just need to, um, we can actually try to find the uniform convergence, and to show, before you go straight to uniform convergence, we need to show that this thing is pointwise convergence. And to show that this thing is pointwise convergence, that means we need this guy here. We need this f of x. Okay? So that means to show, or let me just say for pointwise convergence, for pointwise convergence first, we always have our limit as when n tends to infinity of fnx will always be equals to f of x. Okay, so if the result is 0, then it is pointwise convergence. So now let's look at this. Take the limit as when n tends to infinity of this nx over 1 plus n squared x squared. So now let's show this. Okay, n tends to infinity, that means I need to divide each term by n. So if I divide each term of this by n, let's confirm that the result will give us 0. And if it gives us 0, that means pointwise convergence. So we have nx here, divided by n all over 1 over n. I have n squared x squared divided by n, right? So I think I should use n squared. That would be the best thing. N squared is the highest degree. So I'm supposed to divide each by n squared. That's better. That's fine. N squared is the highest degree. Divide 2 by n squared. So now looking at this, if this cancel this, I'll be left with x over n all over 1 over n squared. And this should be x squared left, right? N squared cancel, I'm left with s squared. So I still have limit as when n tends to infinity in this case. So now the next thing for us to do from here is to write the limit as when n tends to infinity. Okay, sorry, I don't even need that again. Just go ahead and substitute n equals to infinity. And this is x over infinity in this case, all over 1 over infinity squared plus x squared. And anything over infinity is 0. X over infinity is 0. Anything over infinity here is 0. Then plus x squared. Then 0 divided by anything, that's 0. So since the limit as when n tends to infinity of nx over 1 plus n squared x squared is equals to 0, which simply implies that it's also equals to f of x. Then what happens? It's pointwise convergence to 0, which implies that my f of x is equals to 0. Now I have this result first. That means I already have this particular answer here. Oh, I already have this particular answer here in this case. Okay. And at the same time, now let's test for let's use our majorant. Let's Okay, this one is for pointwise convergence, right? For pointwise convergence. Now let's test for uniform convergence. Okay, I think that's what we need next. So then for uniform convergence, now what are we going to have in this case? Now looking of considering this uniform convergence now, we'll have to find, okay, let's bring in our fnx first. My fn of x is actually equals to nx all over, okay, 1 plus n squared x squared. For uniform convergence, I said we need two important things. We need to take the absolute of um fnx, which should be less than or equal to the majorant of n in this case. And at the same time, we now need to take the limit as when n tends to infinity of mn. So if this one converges, so what happens? That means this fnx is uniformly convergent, or it converges uniformly this time. These are the two important things that we need. Okay. Now I can actually take the absolute of this, but I don't know what my mn is. How will you know what to use for mn? It's not that you guess. It's not that you just take okay, mn can be okay n over n squared. Then I can take my mn as 1 over n squared, or I can take it as 1 over n. You don't just assume. We can actually look for it. You can actually look for this mn. And to do that, in calculus, we have what we call the maximum point and the minimum point. I believe you know how to find the maximum and minimum point of a particular function. So whereby you need to find f prime of x, the third at stationary point, your derivative will always be equals to 0. So at the second derivative, you know what to do. If it's greater than 0, that means it's at minimum. So we are not considering greater than 0. We need less than something, right? So we are only going to consider f prime prime of x to be less than 0 at maximum. That's what we This is what we actually need in this case. So from this particular point here, we will have gotten the result for x. So I'm not sure that you really understand that concept until I try it here. But all I just know is that we need to find the stationary point. A stationary point, or you say a turning point. Okay, at turning point. And the reason why I'm doing this is because I want to know what my mn is, so I can go ahead and solve this and then deduce that. So at turning point, or you say at stationary point, the derivative of fnx is always equals to 0. That means I need to differentiate this expression. And if you don't know how to differentiate, na another wahala. So you must differentiate this thing and then you set the result to be equals to 0. After that, make sure you find x, make sure you make x the subject of the formula in that case. And then for me to differentiate this guy here now, I need to calm down and solve it one after the other so that you understand it clearly. If I differentiate this expression here, that is quotient rule. So I have the formula as vu prime minus uv prime all over v squared is equals to 0. My own main target is to just look for x in this expression. After looking for x, you see that your mn will surely come out. So the upper part is u is nx, and my v is 1 plus n squared x squared. So if I find my u prime, this is a constant, like saying you have 2x. If you differentiate 2x, that's 2. So if I differentiate nx, that is n. So let's look for v prime. This is also 0. If I differentiate 1, that's 0 plus. This is a constant. That means I'm only considering x squared. This constant is there. So if I differentiate x squared, that's 2x. So I'm having something like 2n squared x. Yes, if you differentiate this, so I have 2n squared x. Now if I come here and substitute now, I want to manage the board. So my v is 1 plus n squared x squared, right? Let me scroll up a little bit. That's my v. This is my v here. So my u prime is n. So let me just put the n here. Let me put it in the bracket. Minus u is nx, and then my v prime is 2n squared x. Then all over v squared. What is v squared? V squared is 1 plus n squared x squared, then all squared. You know that this result is equals to 0. Now you should know that this is a very complicated simplification. Before you can make x the solution to the formula here, it's going to take a lot of time, but still you need to um, find all means to make x the subject, and I believe it will surely be possible. It can be possible. Now let's try it out. Now looking at this now, 1 times n is n, and then if this multiply this, okay, I will surely have it as, let's say we have plus, I'll surely have it as n cube um x squared, right? In that case, then minus, I also have this expression there. If I multiply this and this together, I'll have this as 2n cube x squared. Now it's making sense. 2n cube x squared. Now this is common, right? So I have 1 plus n squared here, x squared here, then squared is equals to 0. You know, if you drop one and cross multiply, this one will multiply this 0 and then it becomes 0. So then I'll be left with n. I think this and this have something in common. N cube x squared is common. So I have plus 1 minus 1. That should be minus 1 of n cube x squared. I repeat, I have n plus n cube x squared minus 2n cube x squared here. If I add this minus twice of this. Since they are the same, I say you have plus 1x. Let's say all this one like this is x minus 2x. That should be minus 1x now. You see, this and this are the same. So I should be left with just minus x, and which is minus n cube x squared. Then equal to, this multiply 1, I have this. And if this multiply 0, I have equals to 0. So when I get to this point, it's very easy for me to make x the subject. So there's nothing really special in all these things. I have n minus, I'll see, to understand this clearly, I will try to do another example. I will now use the same process. Okay, I'll use the same process. You will now see that it's not something special. Okay, now if this comes, okay, let me just take this to the other side, and I have n equals to n cube x squared, right? If you collect like terms, and if I divide both side by n cube, by what? N cube, this will cancel this, then I'll be left with x squared is equals to, this cancel this, I have 1 over n squared. So if I take the square root of both sides, square cancel square root. Now I'm having my x to be equals to plus or minus square root of 1 over n squared. Now you see this result that you got here, it is our mn. But I've already given you from the theorem itself. It already says for a positive number mn, sorry, not plus or minus, so sorry for that. Okay, this in understanding matters. So for a positive number mn, that's what we have in the theorem. So I can't take negative of, so I'm only considering the positive of that. But all I know is that this should end up giving us square root of 1 is 1, and square root of n square is n. So I'm having plus 1 over n minus 1 over n. So between the two now, which one will you now pick? I will only pick the what? The positive part. So this is just like saying at turning point, my x is equals to 1 over n. Okay, that's for my x1, and my x2 is equals to minus 1 over n. So I'm only considering this part. Okay, I'm only considering this part. My x1 is already 1 over n. So since my x is already equals to 1 over n in this case, then we need to test for the maximum or minimum. My second derivative of any function, in calculus, if you have the second derivative to be less than 0, that is for maximum, max. And if it is greater than 0, that is for minimum. And I think from the theorem we are considering with, we only need this particular sign here, less than. So we are not considering this. Let's just go for the max. And I think this is also part of the theorem. There are many theorems under this uniform convergence. So we used to consider the maximum point at all time for it. So at maximum now, so now let's check. Let's try to verify this. When you have this kind of expression, I already have my x to be okay. I said between these two now, which one are we considering? We are only considering the positive part. Okay. And I also said something. I said this expression here, okay, is always our mn. So I can actually give you a shortcut. Instead of going through all this, there's another way of doing that. But just take note. So my mn is 1 over n, but I already know that x1 is, according to my evaluation, I've been simplifying it since I have my result as 1 over n. So I can't consider the negative part. Let me just go with this. Or the reason why I pick this is because if you go ahead and find the second derivative, and then you want to consider the maximum value. The maximum value is for this one. It's for this guy here. The maximum value is for this guy. And I'm very, very sure the minimum value is for this. And to test that this is correct, this 1 over n is what I use, you need to use find the second derivative. And you know, if you want to go and find the second derivative, it's going to take a lot of time. Okay, I differentiated this one, I have this result. After differentiating that, I think this is what I have. This is what I have. So you seem to differentiate this thing again. So it's going to take you a lot of time. Okay? It's going to take a lot of time. You just go ahead and pick the positive part. That's just the logic I can give you. Mn is always positive. So pick the positive part in this case. But what if you are positive, positive? How will you now know what to pick? Then that's another case. That's another case. Then that is where you now need to find the second derivative. Okay? If this is positive and this is positive, if you solve the equation and you notice that the two is positive, then you don't have any other choice than to find the second derivative and then consider which one will be the maximum value or not. I think maybe I will try to find another way of editing another video based on how to find this maximum and minimum point. I think that's, I'll try to explain that in another video. But for now, since we are considering the positive part, we have this result. So I can easily just go straight to the expression which says that the absolute of fnx, you know, according to the definition of uniform convergence, we always have this expression here to be less than the epsilon, right? To be less than the epsilon. Now looking at this expression here, you know, we can actually have our fn as least this x. Now let's call it x1. Since we already have our point, you already have a point, then this one will also be what, x1 too, right? Less than epsilon. So let's see what is going to happen here. Now looking at this, my fn of x1 simply implies that, okay, my nx, my fnx is nx according to what we are given over 1 minus n squared s squared. Since I now have x1, this one will be x1, this one will be x1. Okay, my f of x, remember that my f of x, what do I have as my f of x? Okay, my f of x, remember that I've done it before. My f of x is 0. F of x is equals to 0, right? In this case, f of x is equals to 0, remember. So if you now to look for f of x1, you know where to put x1 is still equals to 0 in that case too. So as far, it's just as if you have something like obviously x1 is power of nothing. Okay, so when you substitute x1 as 0, since your x1 here is 1 over n, and then you still put 0 here, you still have 0 left. Okay, sorry, anything is power of, okay, that means you have, okay, this is what we have. 0 times anything will shall end up giving you 0 in that case. So no matter it is, if you have the f of x to be equal to 0 and you want to look for f of x1, it is still 0 because there's nowhere to put your x1 in this f of x. Okay, it will still give us 0 in that case, right? So this f of x is 0, f of x1 is 0 in that case. So less than epsilon. Now looking at this clearly, you know, epsilon is a very small number, right? So I can take epsilon to be equals to either, most of the time, you know that we always take epsilon to be equals to 1 over 2. You can use 1 over 3. It's a very small number. You can use it as 1 over 4, 0.001 or something like that. It's a very small, epsilon is a very small value. So you can take epsilon to be anything, either 1 over 2 or 1 over 3. So in this case, I'm considering 1 over 3. Okay. Now, what is my nx1? My x1 is 1 over n, right? Times 1 over n, then all over. This one is 1 minus, I have n squared here. Okay, my x1 squared means I have 1 over n, then all squared, and that's 1 over n squared too, minus 0. So let's confirm that this thing is less than, taking epsilon to be, take epsilon to be any of this value, but I'm considering 1 over 3. Okay, let's check for 1 over 3. Now looking at this, n cancel n, I'll be left with 1 over 1. Is this, okay, this thing that we actually consider, is it 1? Let's check our function again. Is it plus or minus? Oh, sorry, it is plus. So I have to correct that. So this is plus. Okay, our fnx is plus, please. Let's correct that. So that's plus. So this one is also plus here too. So that's 1 plus. So if this cancel this, I have 1 minus 0. Let's confirm, is this less than 1 over 3? Okay, now let's confirm. 1 over 1 plus 1, that's 1 over 2. 1 over 2 minus 0. I take the absolute less than 1 over 3. So let's confirm. So it's 1 over 2 less than 1 over 3. That's the question now. Even though you use 1 over 2, is 1 over 2 less than 1 over 2? No, they are equal. So I think this is just, it is absurd. So since you have 1 over 2 less than 1 over 3, 1 over 2 in decimal, I think that's 0.5, if I'm not mistaken, right? So you can actually punch that into your calculator and confirm whatever you want to value. If you have 1 divided by 2, that's 0.5 in decimal. And if you have 1 divided by 3, that should be 0.3. So is this thing true? How can 0.5 be less than 0.3? So since this is not true, okay, automatically speaking, then we can actually say that um that fn of x can actually say that that fn of x is what? Is not uniformly convergent, okay, or it does not converge uniformly. So that's how it works. So in this case, I can just make a round-up expression, so which is not true, which is not true. So in conclusion, we say that there is no natural number n, there is no natural number big N such that this equality holds. So I think that's what they ask us to prove. So there is no natural number that satisfy or that makes this thing holds. It does not hold. So that's how it works in that case. Okay. So I think that's all for now. Thanks for watching.